So today's topic is kind of finishing up the match moving chapter. And so where we stopped last time was talking about the process of calibrating an image sequence, right? So we talked first about calibrating a stereo rig, how that would work. And we talked about how basically if I were to show the cameras a kind of checkerboard pattern, wave it around, what I would do first is I would estimate the camera calibration matrices for each of the two cameras, and then I would do the singular value decomposition on the fundamental matrix, and I would use that to find the two camera matrices up to kind of a rigid motion of the world. So now what we want to do is we want to extend this, and we have more than two cameras, and we're moving the camera continuously through the space. And we kind of talked about the first step of that last time, which was called projective reconstruction. And we learned that at the end of the projective reconstruction process, probably what I would get would be this weird, I would get a set of cameras and a set of points such that the projections of the points onto the cameras would give me something that would be close to what I observed. I'll write this down in just a second. But that probably what I'm going to see in terms of the capital X points is something kind of weird like this, right? The structure of the scene is not going to be, really accurate in terms of perpendicular and parallel lines. It's going to look probably pretty strange. And so we need to undo this in the first step I'm going to talk about. So again, kind of what was the reason for this? Well, at the end of projective reconstruction, what I have is for every, this is like a 3x1 image point in homogeneous coordinates. For every camera matrix I have and every scene point I have, at the end of the projective reconstruction process, these, on the left-hand side and the right-hand side should be roughly equal, right, if I've done a good job. That means that these are the points I actually saw, and these are the points that I would kind of predict if I said this was the camera matrix and this was the 3D scene point, right? And the problem was that, and if we kind of remember how this worked, the idea was I had this big, measurement matrix, and I wrote it like the product of a bunch of camera matrices and a bunch of scene points, right? So this was like some 3m by 4 by n matrix. This was a 3m by 4 matrix. This was a 4 by n matrix. And we showed that basically we could exploit the fact that we knew that this big measurement matrix only had rank 4 in order to find a good candidate set of p's, these are the cameras, and a good candidate set of points, these are the x's. But the problem is that I can put some, 4 by 4 matrix in the middle here. I could say this is H inverse. So again, I can choose any non-singular matrix H here and still have exactly the same measurement matrix on the left-hand side, right? So that's the problem with projective reconstruction is there's no way for me to resolve this ambiguity without knowing more about what's going on in the scene, okay? So that's the topic of the first part of the lecture, and it's a little bit mathematically hairy, so I may gloss over some of the parts that are really, really tedious. You can look at those in the book. But I'll give you the kind of broad strokes of how this works. So kind of the preview is that, the idea is that the camera matrices that come out of some kind of arbitrary projective reconstruction are probably going to be pretty strange, right? In the sense that without telling so far we haven't used the information, for example, that I know that the, pixels in a real camera are usually square, right? So that gives me some degrees of freedom that are removed, and I can use those to force constraints on the resulting values of this H matrix. And the same way, maybe I have some additional sign information that, for example, I know that for most good cameras, the principal point, which is the place where the z-axis intersects the image plane, should be right in the middle of the image, right? That means that, the 0, 0 point is right in the middle of the image. Again, for high-quality cameras, that's also usually true, or pretty close to true, right? And that, again, gives us some more constraints on what these entries of H could be, okay? So that's the setup, okay? So how do we actually go about, resolving a good H that will solve our problem, okay? Well, to make this a little bit more precise, let's say that I got the set of cameras from, projective reconstruction. And now what I want to do is I want to kind of transform each of these cameras by this matrix H that I'm going to have to figure out. Again, this is a 4x4 matrix H. And again, what I want at the end is that this gives me a Kerr matrix where this K is in a form that makes sense to me. Okay, that's the kind of fundamental idea. I know that any, like you're doing in the homework, any 3x3 matrix can be decomposed into a triangular matrix times a rotation matrix, but that doesn't mean the triangular matrix is exactly what I want. What we're doing now is we're forcing that triangular matrix to be what I want. Okay. So on paper, basically since H is got 16 elements and it's non-singular, that means it has 15 degrees of freedom. So there's lots of possibilities for what this possible H could be. We can immediately remove a couple of them by, saying, okay, well, there are some of these H's that are purely going to do a rigid motion of the scene, right? So it's like I could take all the cameras and all the points and just change my frame of reference. That in itself has 6 degrees of freedom. Or I could make the whole thing, scaled differently. That would be another degree of freedom. So what I can do initially is I can say, okay, what I want to do is, remember last time we said that I could force the first Kerr matrix to be basically a simple identity matrix followed by a bunch of zeros, right? Now here, I know this is not really the true Kerr matrix because this kind of implies that the calibration matrix, the K matrix, is the identity, which is probably not true, right? What I want is that after I do my transformation, that I get the first K, which I don't know, and let's assume that I still have the rotation matrix lined up with the world coordinate systems and the camera center at 0, right? So let's think about how this would work, right? So this is like saying that after I apply the H, this is going to be the form of my new camera matrix for image 1. And so that means that if I have P1H, that's going to be the identity matrix times with a 0 matrix. And then I'm going to split H into a little block matrix. So here, this is going to be 3x3. This is going to be 3x1. This is going to be 1x3. This is going to be 1x1, right? So this way I'm taking the 4x4 elements of H, and I'm kind of blocking them up so that I can multiply them by this matrix. And so now I see that if I put these things together, what I get is I get A, and let me do this for a second. I get A, B. That's it, right? So now I compare this to this, and I say, okay, well, that tells me that actually this A has to be the same as this K, right? So that tells me that already I can remove some degrees of freedom here because I know that this A, which used to be a 3x3 matrix, is now actually going to be a camera calibration matrix, which means it really only has 4 or 5 non-zero elements. And then comparing this to this, I say, well, that means that B has to be 0. Okay, so I've already removed a whole bunch of degrees of freedom with this kind of normalization saying the first camera has to be in a fixed position. And since I want this to be a non-singular matrix, I'm just going to, force D to be equal to 1, right? And that way, since this is non-singular and this is 1, I'm always going to have a singular matrix, or a non-singular matrix. And so if I kind of think about what that means about H, that means that H has a particular form. It has a camera calibration matrix here, it has zeros here, it has some vector here, and it has a 1 here, okay? And this K matrix, right, has to be of the form that we kind of know, where I've got the focal lengths and the principal point, and these entries here are 0, right? So there's really only 4 degrees of freedom here, and there's really only 3 degrees of freedom here. So I've already removed lots of degrees of freedom from the problem. Now I've only got 7 left that I have to figure out. And I'm going to just make this a little bit easier by renaming this C to be something that's in terms of K. So this is, I'm going to be doing a little bit of a jig here to make this easy for myself later. So here, K1 is this, and V is some 3x1 vector. Okay, so now this is where things get a little bit hairy, okay? And so let's see how hand-wavy I can get without losing the intuition. So now what I want to do is look at the rest of the camera matrices, okay? So I've kind of used the first camera by fixing its kind of position in space to make my life a little bit easier, but now the rest of the cameras, 2 through N, or 2 through M, I'm sorry, you know, I have to deal with those kind of generically. So let's suppose that before I did this estimation, I had something like this, right? So for the remaining cameras, I have, you know, some generic 3x4 matrix. That's what came out of the projective reconstruction, okay? What I'm going to do is state without proof a couple things, okay? The proof is kind of a homework problem in the book. So we can show, first of all, there's this very important concept that we talked about last time. Well, we kind of, okay, I guess I can't say we talked about it too much. When we talked about the plane-based camera calibration algorithm, we brought up this concept of this thing called omega. So if you look back in your notes, you should find something that looks like this. So this is basically saying that if I take the camera calibration matrix and I multiply it by its self-transpose, and I take the inverse of that, right, I get this special 3x3 matrix, okay? And we use the fact that the elements of this special 3x3 matrix were what we used to put constraints on the plane-based camera calibration, right? So the idea is that this 3x3 matrix can't be arbitrary. It actually has a special form that comes from the fact that there are a bunch of zeros in this triangular matrix, okay? And so if you look back in the book, you can find the formula for omega in terms of these parameters, okay? So, and this is true, so there's basically one of these omegas for every camera, okay? And what you can show, and this is the part where I'm waving my hands a little bit, is the following. And for this, I'm going to bring my book over a little bit. So let me write this down first, and then I'll kind of interpret what this means. So what's the deal with this? This is basically saying that every camera's omega matrix here is related to the camera matrix that I estimated from projective reconstruction, right? So this is going to be 3x4, this is going to be 4x3, and here is some special 4x4 matrix in the middle. And this 4x4 matrix in the middle only involves this stuff, the V and the omega 1, which is what kind of is involved with the original parameterization of this H, right? So basically, H depends on the camera calibration matrix of the first camera and this V. So I also have this omega 1, which is K1 transpose inverse. And so the idea is that, you know, all of the stuff in Q only depends on entries of H, which in turn involve K1 and this unknown vector V. So this getting from here to here is a homework problem of why is this true. And it's not hard to show, actually, once you actually start to work out, you know, if you work your way backwards, you can show that if I know, so the form of Q is given in the book. So the form of Q is, well, I'm not going to write it down, but it's explicit. Well, I guess I will write it down right now. So the form of Q is this. Oops. And you have to write this stuff down. This is in the book. Right, so in this form, you can see that here, this Q matrix only depends on omega 1 and V. And if I were to multiply all this stuff together and crank this out, you would find that on the left-hand side, I would end up with the omega I for the ith camera. Part of the way that this works is that, the PI only involves, KI, a rotation matrix, and a translation vector. And there are going to be cases where the rotation matrix kind of multiplies by itself. I know that's the identity matrix, and so that's where things go. Question?
So I'm a little confused as to why omega 1 is involved for every single omega I. I guess I don't really intuitively see how that makes sense.
Yes, okay. So why is omega 1 involved for every single I? Well, let's see if I can convince you. Pause for a second and think about why this is true. Oh, yes. Okay. This is a little bit tedious.
It's in the book.
It's in the book.
Read the book.
Yeah. I hate to just defer you to the book.
Can you give like a little intuition?
Right. So let me just write down a couple of the key steps here. And then you see if I can prove the intuition of a couple of these key steps. Okay, so the key question is, why is that thing true? So let's think about it. So what I have is, I have AI transpose, and I multiply that by my H, right? So my H is in the form of this. Right, so this is the special H that undoes the projective thing. So what I get when I multiply these things together, I get AI K1 plus minus AI V transpose K1 AI. Right? After I undo this, right, what I have to get is the camera matrix for the ith camera, right? And so if I compare this to this, right, I see that the camera matrix for the ith camera kind of involves K1 and V because of the way I parameterized H, right? So that's kind of because I chose H in a way that depended on everything from the first camera, right? And so then once I've got this, I guess that's what this shows. And then I can say, okay, well, what would I get if I took this this times this transpose? I would get omega I inverse. And so this times this transpose, right? Actually, I guess I kind of proved it, right? So this thing times this transpose is exactly K1 transpose AI minus AI B transpose, right? This, on this side should be omega I inverse. This here is omega 1 inverse. And I think I proved what I set out to prove, right? So that's exactly what I said here, right? Okay, so that wasn't that bad. A little bit weird, but I did it. I'm proud that I can still pull it off after not thinking about it for a while. Okay, so where does this get us, okay? So now what I have is I have a relationship between this 3x3 matrix for a given camera, the projective matrix that I estimated, this 4x4 matrix that's going to be important, that depends on H, and this guy here, okay? And so here's where I'm going to use the constraints on the camera calibration matrix that I'm going to say, hey, I can't have bizarro cameras, I have to have cameras that make sense, okay? So for example, let's suppose that I knew that I had a really simple camera calibration matrix like this, right? I had alpha x, alpha y, 0, 0, 1, right? So this is kind of like saying, you know, I know the principal point is in the middle. I know the pixels are square, right? In the real life, I may not necessarily know the principal point is in the middle. Let's assume that for the moment, right? Just to kind of motivate this. So let's suppose this is my k. And then let's suppose that I look at the form of this omega, right? So what I need to do is ki transpose inverse, which is, this is a really simple matrix to multiply by itself. I'm going to alpha x squared, alpha y squared, 1 inverse, which is equal to 1 over alpha x squared, 1 over alpha y squared, 1, right? So the idea is that I look and I say, oh, on the left-hand side, I've got a matrix that is very simple, right? Lots of zeros. And on the right-hand side, I have something that depends on the camera matrix I've got and this Q, right? And now I can think about what is this Q, right? I can also show that Q, if I make the same assumption about the first camera matrix, has this particularly nice form where I've got 2 entries along the diagonal that are equal to each other, a 1 here, and then I've got some more numbers here. Right, this again comes from the fact that if I assume that K1 is equal to something like this, then when I multiply all this stuff out from here, I get a particularly nice looking Q matrix. And now the idea is, okay, well, there are only a few things I don't know, right? So again, it makes sense there are 5 numbers here I don't know because there were 5 numbers back here that I don't know, right? I don't know the alpha x and alpha y for this matrix. I don't know the 3 values of this vector v. So there are 5 degrees of freedom I have to estimate, and here they are in a slightly different form, right? And now I can use the fact that I know the structure of this, I know the structure of this, to make my life easier. So for example, I can say, okay, the fact that, actually, I think this gets even easier because if I were to assume that these pixels had the same aspect ratio, so if I assume that the pixels are actually square, then these numbers are actually the same. And then I have even more constraints. I can say that number 1 constraint is that this thing equals this thing. So I could say that on the left-hand side, I must have that kind of the 1-1 entry has to equal the 2-2 entry, right? That's one constraint. Another constraint is that I have to have zeros in these 3 places, right? So I have to say that the 1, 2 entry is equal to 0. I don't know why I did this. And I could also say that the 1, 3 entry is equal to 0, and that the 2, 3 entry is equal to 0, right? So fundamentally, I have 4 constraints on the left-hand side, and you can imagine that those put constraints on the Q on the right-hand side. So if I were to write this a little bit more nicely, what I would say is that, you know, 4 constraints on omega I, which come from the form of the known camera calibration matrix, lead to 4 constraints on the 5 unknowns of this Q matrix. And it turns out that you can form up like a big linear problem. You can form up a big linear system for these Qs in terms of basically known values of the PIs, right? Because if you think about it, what I'm doing is I'm saying, okay, I don't know what these numbers are on the left-hand side, but I know that these 2 are equal, right? And so that equality forces something that has to do with the P's that I have for my projective reconstruction, these unknown things, and again, I know these over here, right? So if you work it all out, you end up with basically 4 equations in these 5 unknowns. And so that means that if I'm assuming that I fixed the first camera, that means I need at least 2 more cameras in order to estimate everything, right? So that means I need at least 3 cameras to get a solution. And again, as with all these things, the more cameras I have, the better I can do with a least squares solution. And the process of obtaining this is kind of similar to, for example, how we estimated the fundamental matrix, where we have this direct linear transform, where we form up this linear system, we solve it, and then we put on some more constraints that we know need to happen. And so basically, then I work my way backwards. So then, then I get Q. I undo this to get, H. And then I apply H to each, PI to get what's called a Euclidean reconstruction. So that's kind of the very broad strokes idea of how this works. Okay. Now I'm too warm. Maybe it comes from sweating out that derivation here. Not easy. All right. So after this process, hopefully what I get is something that turns this warped house into this nice house, right? So what I'm going to get is something where, again, I can't expect that I get the 3D coordinates of all the points in the actual world coordinate system because I don't really know the relationship between the first camera and the world, but I get something that is off by the truth by this nice rigid motion and scale, right? If I were to say, okay, by the way, this, wall of this house lined up with the x-axis or the xy plane of the world, well, then I could kind of warp things back to entirely the right coordinate system. So this is kind of the big picture of how it works. In order to do this derivation, I made some assumptions, right? So for example, to get here, I assumed that the camera calibration matrix had an extremely simple form, right? You could also do it if I don't know, for example, that the principal point is at 0, 0, or if I have some crazy camera where I, don't know the pixels are square, right? So the less I know, the more cameras I need to be able to solve for all the unknowns, but the mechanism is pretty much the same. Okay. I feel better now. So comments or questions about that? Again, to really understand, I think you have to kind of work through the math yourself to see how things all fit together, but that's the big picture. And so fundamentally, this is, so remember what I said last time is that really what do I want to actually do, right? What I want to actually do is solve this kind of minimization problem as well as I can. I have all the cameras, all the points, and I want to minimize the difference between, I guess the way I said it was, I have a kind of indicator function that says, did I see point ij, did I see point j in the ith camera? And then I had a distance function where I wanted to look at the difference between the projection and the, model for where that worked, right? And so really, I can treat everything that came up to this point as a kind of an initialization for this problem, okay? Because even after you do this Euclidean reconstruction, you're going to find that things are still not as good as you could get, okay? What we want to do really is we want to minimize this kind of cost function to get the lowest possible value, right? And so what I can do then is what's called bundle adjustment. We talked about this last time, where the idea is that the bundles, right, are, going the wrong way. The bundles are like these rays that are coming from the camera centers to the points in the world, and I want to adjust these bundles to line up as well as possible with the observed feature locations on the image plane, right? And typically, you could say, well, why didn't you just solve this in the first place, right? I mean, why couldn't I just throw all my points and stuff into this cost function and crank it out, right? The problem with that is that this is a huge dimensional problem, right? If you think about, I have maybe 100 cameras, so that's, going to be at least 10 parameters per camera, and then I've got maybe thousands of points, right? So I've got this huge dimensional cost function. It's very difficult for me to know even where to start looking in that space, right? And if I don't have a good initial estimate, I'm probably going to end up in part of that space that is going to give me some local minimum, but not anywhere close to the truth, right? That's why this initial phase of projective reconstruction and Euclidean reconstruction is important, because it gets us into the right neighborhood, right? Then I use that point to initialize the minimization of this thing, which is just kind of like a standard kind of nonlinear minimization. So if any of you have ever done like Levenberg-Marquardt, does that sound familiar? So if you ever used MATLAB to do like nonlinear optimization, there's this, nonlinear, F square nonlinear, no. Anyway, so the point is that if you ever done optimization, you will learn very quickly that if you don't start close to where you want to be, you're going to have a bad time. So this is the idea, is that we use the endpoint of this kind of projective to Euclidean reconstruction as a starting point for this optimization. And so this optimization basically proceeds kind of pretty normally. The main thing that I want to do is I don't want to lose my... So in Euclidean reconstruction, I was really careful to force the camera matrices to look like what I knew they should look like, right? I said, okay, I have some constraints on these camera matrices, and so it's important to enforce those constraints as well as possible by correctly parameterizing these things. So for example, I really don't want to use just 11 numbers, arbitrary numbers, to parameterize P. What I want to do is I want to say, okay, this PI should be parameterized, kind of what I would say minimally, by, basically I have a couple parameters for the aspect ratio and the focal lengths. I have the principal point. I have basically, let's say, 3 numbers for the rotation matrix. And I have 3 numbers for the translation, right? And if I know further information, for example, if I know that these 2 things should be equal, or that this is exactly 0, then I should definitely not include those as degrees of freedom in estimating P, right? And again, just to make sure I've got some sort of a unique solution, I would use the same trick of saying, okay, the first camera should be at the world origin, and the second camera, I could say, is like, so what I would say to minimally parameterize and say the first camera should be at 0, 0, 0 with an identity matrix, and then I could say to avoid any ambiguity, I could put the second camera matrix exactly 1 unit away from the first camera matrix, right? So there's basically, I don't know how far away it is in real life, but I assign a scale by saying my scale of the problem is that the 2 camera matrices, 1 and 2, are 1 unit away in world space. That eliminates the possibility of things being bigger or smaller, right? Okay, and so this, the book goes into the details of how I would do all this setting of parameters, right? And then for each of these guys, I parameterize these with a 3D location in space. So parameterization is important, and actually, if you really dig into this problem, it turns out to be a fairly subtle problem. There are a bunch of unfortunate things, like, for example, you would hope that if I were to just like switch the order of all the cameras, say, okay, now you camera 14, I'm going to call you camera 1 and renumber things and re-optimize. You would hope that if you did that, it wouldn't have any effect on the solution, but unfortunately it does, right? And so these things are called gauge freedoms and gauge issues, and really understanding them is an extremely subtle problem. And so I think that in real-world applications, you kind of just, you accept the fact that maybe things would have been different if you renumbered the cameras, but it's not a big enough difference for visual effects that we care about, proving anything mathematically. So the final thing I want to say is about this is that, there is a huge dimensionality of this problem, right? So, like I said, there are possibly, tens of these and possibly hundreds of those, right? So there's lots of degrees of freedom of the problem. And if you try to solve the problem without thinking about how it is structured, you'll end up with these massive matrices, and it will take you a very long time to solve, right? But one thing to observe that makes the whole problem a little bit more tractable is that each xij, each measurement, only depends on camera pi and point capital Xj, right? I mean, worst case scenario, it's possible that every measurement that I have could depend on all the parameters I'm trying to optimize over, right? In a generic optimization problem, that might be true. In this case, the idea is that actually, everything that I see only affects a few parameters of my optimization, right? Which means that I can get away with parameterizing things, or I can get away with kind of, how do I say this in an easy way? So let me think about it this way. Suppose that I have a matrix that tells me, okay, suppose I have 3 cameras and 4 scene points. Okay. And then I have, say I have each of these points is seen by each of these cameras. And so I have 12 numbers down this axis here. I guess stuff like this. Right? So it is that, this guy here only depends on camera 1 and point 1. This guy here only depends on camera 2 and point 1. This guy only depends on camera 3 and point 1. This guy only depends on camera 1 and point 2, and so on. So there's this kind of like sparsity to the way that things depend on each other, if I'm being really sketchy here, right? Worst case scenario, all the measurements could depend on all the parameters. But in this case, that's not true. And so this matrix here of what depends on what, one way to think about this is called the Jacobian, right? So if any of you have ever done any sort of, if you think back to, I'm not sure where you would have seen the Jacobian in like multivariate calculus, but I mean, there is a, I'm trying to think of whether you would have seen it in multivariate. Given the blank looks, I'm assuming you didn't see it. But this is a common term from optimization, right? So basically, the observation here, since if you haven't done optimization, then I don't want to go too far on this, but the idea is the Jacobian is what's called sparse, meaning that it has, many zeros. And the fact that it is sparse means that I can solve the problem in a much more efficient way than if I had assumed this was just some arbitrary big matrix full of numbers, which is the way that if you just turn the crank in MATLAB, you might end up solving that problem. Okay, and so I think that the main thing I want to say about this then is that we should exploit this in the optimization part, in the bundle adjustment. And so the best algorithms are using the fact that, there's this kind of sparsity to this Jacobian matrix, and that makes the solution process much more efficient. Okay. So without going into the details of the optimization, I think you can read that in this section. You can kind of read about, okay, so, many of you probably in calculus, certainly in calculus you took the derivative of things that equals 0, right? So in the same way, when you're doing multivariate optimization, you take the gradient of something, you say equals 0, right? And so in practice, you can't solve that system exactly because it may be nonlinear, and so we find different approximations to solving that system. One of those well-known approximations is called the Levenberg-Marquardt algorithm, which is kind of this iterative process of getting to the minimum of a function, and that iterative process involves this matrix, is what it comes down to. So I would suggest taking a look at this chapter, and also there's some stuff in the appendix about numerical optimization, that when you're actually faced with solving a big problem like this, you kind of have to know what is your plan of attack. Okay. So let me talk now about what we actually see as results, right? I guess that this has been a little bit dry in the sense of not actually seeing any match moving results. So let me see how this works. So I took a video. What? Why you suck? Can I open this with the... So on a snowy day, I took this video, and you can see, first of all, that since I was not wearing a Steadicam, that there's like this horrible shakiness to the video, right? But what I'm doing is I'm walking around this structure. There's lots of nice texture on this building, right? So I should have a good hope of trying to, number one, reconstruct my camera trajectory, and number two, reconstruct points on this building, okay? And so for the audience out in internet land, this is a building on the RPI campus. I took many, many pictures of this building for research stuff. Right, so I'm walking around this building, okay? And so what I hope to reconstruct is basically the 3D points on the building, and there's not really that much else in the scene that I could expect to reconstruct very well. And my camera path, okay? And I'm going to stop it here because we get the idea. Okay, so first of all, let's see here. So here's some pictures of that walking along. And so here is a plot of basically, for every feature point that the match moving software automatically found, how many frames was it visible in, right? And so here you can see that, you know, since points are constantly moving in and out of the camera view, it's not like there's a point that is really visible throughout the entire image sequence, right? Really, I only get to see a point for, say, you know, tens or hundreds of frames, right? And so this is another thing that makes life a lot better from a sparsity perspective, is that, you know, the points and the tracks, you know, don't persist throughout the entire sequence. So this makes life even better in some sense for the numerical optimization, because if I saw the points in all the frames, then life would be much more, you know, numerically complicated, okay? And so here is a result that I got out of applying a match moving software, right? So what you see is this every red dot here, which makes this kind of red line, is a position on the camera path. The red line sticking out from every dot is the camera orientation. And the blue dots here are 3D points in the world that have been reconstructed. And so you can kind of see that this worked reasonably well, right? So what you're kind of seeing here is if you can kind of pick out the you know, the floor plan of the VCC from the top, right? So this is the left wall, this is the little part that sticks out, right? This is the right wall, and this is the part that, you know, is near the MRC. And so I think there's another point of view here. Here I'm kind of looking at it from the side, right? So here, this is like the vestibule of the VCC, right? And this is the right-hand wall. And you can kind of almost see even that there are these points here that kind of correspond to the window and the peaked roof of this, right? So it's kind of hard to visualize once you get this 3D point cloud of whether you, I mean, if you know the environment, you can say, oh, okay, this looks pretty good, right? And so, you know, this looks pretty good. I made a ground plane here to kind of make it clear what the building is lying on, but this is the result that I got. And this is kind of what you see as you run the match moving software. So for this I used a tool called Buju. This is one of the ones that came out of the University of Oxford and was spun off into a company. And you can kind of see here, I'm going to play the video in a second, but what you kind of see here are there are these yellow points. Let me try to make this a little bigger. Right, so you can kind of see the feature points that have been chosen to be automatically tracked, right? So I didn't make any intervention, I didn't do any intervention on this. I just kind of said, okay, you know, track whatever points you can. And then what you see here are these green kind of what I would call test objects, right? So the idea here is that to tell whether your match move is good, what you can do is you can insert some artificial things into the world, and if you did it right, they should stick, right? So for example, I said, okay, I want to have a sphere that is 1 meter in diameter sitting at point, you know, 30, 40, 50 in my VCC world, right? And so as I move the camera, this stuff should appear to stick to the environment. And so let's see the video where I tried to do that. Okay. So here, what you see is that you can see, number one, the yellow feature points that survived all the outlier rejection processes, right? So this is the stuff that's being used as the basis for match moving. You can see they come in and out, you know, like, and, you know, there are points that you might think, why didn't it track that? You know, you can't really tell, right? But it's got a bunch of points in every scene, and you can see that the green objects are kind of sticking correctly, right? So for example, this green sphere does appear to be kind of floating in air in front of this window in a natural way, right? And so, of course, in a visual effects scenario, this would be a creature or a monster or something instead of a green ball, right? But this is just for the purposes of testing, right? It tells me that my estimated 3D coordinate system is correct. Another thing that you can't do at this stage is, I guess I was kind of smart here. So basically, here as we travel around the building, I'm sticking different objects to different points on the building. So here's a good example of like, what's up with this cone? This cone, or this pyramid, it seems to be penetrating through the building surface, right? And the reason for that is that, right now, the match moving software has no idea about actual physical 3D structure, right? All it knows is that there are these points in space, right? And so when I put a test object back in space, for me to render that test object to appear to physically pass behind objects would mean that I have to do some sort of like matting and segmentation of the front of this building, right? I have to say, okay, now I would have to apply some sort of algorithm that says, okay, if this is the side of the building, right? There's nothing in the software that knows about the 3D structure of things. And so all the test objects that I put in are going to be effectively kind of like see-through, or they always appear to be in front of all the other pixels on the image. But, you can see that points kind of make sense. The test objects are not like jiggling around on the surface, right? You can kind of see, for example, that this test object really does stick pretty well, even though the camera's jiggling around, that it doesn't appear to slide off of the surface, right? That's how I can tell that I had a good match move, right? And so hopefully you can achieve something kind of similar as you try and apply this to your own footage in the homework, right? So I think that every match moving software should allow you to put back in some very simple test objects to verify that the match move looks good, right? And probably match moving software also has some tools for you to, for example, after you've done the match move, to go in and place like the ground plane, and maybe also you can say, okay, I want the XZ or the YZ plane of the world to be aligned with the front wall of the building that I'm scanning, stuff like that, right? Yeah, so that was my, crude attempt at match moving with my own, software. This is kind of, what is this? Oh, I see, I'm kind of like this. Right. So these are just some still images of the movie that you just saw, showing that these test objects are sticking to the building. And then the same idea applies when you're doing match moving for, I don't know why this is not what I want here. Match moving for movies. So here, this is from a video that I showed earlier in class of, one of the most recent Transformers movie, right, where they're taking raw footage of Chicago, I think, and so they took lots of helicopter footage of kind of dramatic swooping shots around buildings with no Transformers, right? And then they track points on the buildings, and then they can use that to make the, inserted objects appear to kind of hover in the air naturally. In fact, actually, if I have a little bit of, if I had the foresight, let's see if I still have the presentation from before. See, these movies will play. So now we know a little bit more about match moving, right? So this is the raw footage. You can see, again, there are lots of corners in the background and so on that we can use to do the feature tracking. And then, once you know where all that stuff is and you've estimated the camera move, then you can make this object, you can say, okay, I want that to be basically stationary in 3D space at this point, and it looks like it sticks to the world at the right point, right? And this is kind of an example from very similar to my shaky cam footage, right, of match moving in a parking lot and inserting this 3D car to make it look like it stays there, right? So, I mean, fundamentally, this is the same idea that we just talked about, right? The only thing you didn't see here are the feature points that are being tracked, right? But still, it's very much like the VCC example. And then this is just the example from, what's another case where you might want to do this is set extensions, right? So here, this is from A Beautiful Mind, right? Where Russell Crowe is on this like very small Princeton set. The camera pushes in on the window. You use match moving to track how the camera moved, and then you also have some 3D points on the surface of this thing, and you can use that to figure out how do I put in a bunch of other 3D structure that follows along in the right way, right? So it doesn't need to be some sort of like fantastical creature effect. It can just be things like extending the set that you didn't build, right? So that's a very common thing to want to do. And so these days, basically, I think that at a big visual effects house, I assume that every shot that comes in is kind of automatically camera tracked as kind of like the first step, right? Just to, they probably do they probably estimate the lens distortion, and they probably do the match move, and then that information is passed off to all the other people who have to generate the effects on top of that. Okay, so let me see. Questions about that process? Again, it's not quite as swimmingly easy as it appears to be in my little, 10-minute demo, right? So, I mean, if you read in the interview section of the book, there is, some discussion about, it's hard to tell a priori what will, how easy it will be to match move a given shot, right? You might say, oh, this is going to be no problem, and it turns out to be like a 5-hour nightmare, or you could say, oh, this is going to be really hard, and it takes it, it does it right off the bat, right? So it's kind of hard to guess how it's going to work. There are lots of tricks, like one person mentions, if it doesn't work when you run the camera, if it doesn't work when you run the video forwards, then why not just run the video backwards through the same match mover software and see if it works, right? Then you can just undo the trajectory, right? There's no reason why you have to do it in order. And there's also kind of an interesting story about, it used to be, before the days of camera tracking software, that, you had to do this by eye, right? Which is like this incredibly laborious process, right? There's this story of, one guy told me a story about a shot where you were kind of passing along, it was like a long shot along an ocean liner. And the idea was that there was a SUV that took the place of a lifeboat. And the premise being this was like a super safe SUV, right? And so for that, you have this long shot. Everything has to be right, for like 30 seconds of a whole long pan. And in those days, you just kind of had to keep on jiggling the 3D position of this SUV until it looked correct. And you might find that everything looked good for the first 30 frames, and then it goes off. You have to start all over again, right? So I mean, but there are very experienced visual effects people who can do stuff by eye if at all necessary, right? That's the way they used to do it prior to the commercialization of this kind of software, right? Okay. So I think the last thing I want to mention here is that there are a couple of extensions to this that are kind of fun. And actually, maybe I can just go to them instead. So one is... let's see, I guess I didn't have a Explorer window open. So one is called Phototourism. So the idea here is kind of what I was talking about. Oh, live demo. I don't know if I can do this with my... I'm not sure I want to hit this button because I don't know what's going to happen. But let's see if we look at the short video here. Why you suck. Let's see. How can I do this in a way that...
If you open it up with the regular desktop one, it'll play, apparently the modern one doesn't play.
Yeah, but I'm in the desktop view, right? So I have to kind of figure out... let me try this again. Let me save it. Okay. All right. Don't know why I have to do all this myself. Okay. Okay. So here's the idea: is that you type in a keyword. So the person typed in Trevi fountain, right? You get all these Flickr images, if anyone still uses Flickr. And so, there may be shadows and people in the pictures and stuff like that, but then you can generate this, this is the 3D scene, and you can see the camera positions that were generated from these positions, right? And so this is kind of like, this is very much like what we just talked about, bundle adjustment, but the difference is that these cameras are not in any sort of order, right? So the idea is that you would not be able to have any assumption about spatial or temporal coherence between the cameras. But it's still pretty slick. And so this was already, like almost, well, I guess it's like 8 years ago, right? So certainly life has moved on since then, and there's some other stuff, like I'm not sure where this is going to come up. Right. So in order to, make this computationally efficient, you need to have like lots of computer horsepower to do, right? So here, this is building the Coliseum. You can see there are probably thousands of cameras in this situation, right? And so there's lots of work on kind of like cluster and grid computing algorithms to make this large-scale bundle adjustment problem easier. So if you're interested in stuff like parallel computing and stuff like that, there's lots for you in this area, because it's kind of neat to think about how can you farm out different kind of match-moving type problems into different processors. And so the joke here was building Rome in a day. The idea is that, if you wanted to reconstruct, I'm not sure if they did the entire city of Rome, but the idea was, could you do it computationally within 24 hours on some like mega cluster of computers, right? And so that's what this one was. And this is kind of similar to phototourism that we talked about before. One thing that is a little bit different from this type of work is that if you have a camera, or if you have an image that is no good, right, because it's too dark or there's too many people in the way, in this case, you're not under any obligation to use all the images that you're given, right? That's not really true in camera tracking for visual effects. In visual effects, you can't afford to just say, well, I can't figure out what to do with this image, I'm going to throw it out, right? You're forced to do something good for every image that you have, right? So that's one difference here, is that some of the idea behind this approach is that you begin with a set of cameras that you think are going to be really good for the problem, and then you fill in the rest once you've gotten a good set of initial cameras that they call the skeletal set. And so that's kind of fun stuff to read about. Another thing that's kind of interesting is SLAM. And so, again, I didn't prepare anything, but let's see if we can find a SLAM robotics video. I'm not going to do slam dunk robot chicken. Let's see what this is. So here, this is a, why does it suck? Try this again. There we go. So this is a robot that is moving around its environment and mapping it out. So you can see that the green thing is the robot and the blue points are being, in real time mapped out by the robot as it moves. And so the robot presumably just has a camera on it. And so this is fundamentally similar to a camera tracking problem, right? Where you've got the robot moving around, it sees image points, and then it uses that to build a map of the world, right? There are some differences between SLAM and structure for motion, though, in the sense that here, for example, the robot is probably constrained to be moving on the ground plane, right? So you already have a big constraint on where the possible cameras are. You just have to estimate the basically XY position at every point in time. Whoop, we had some sort of disaster there. The other thing about SLAM that's a little bit different is that the robot probably has some sort of odometry on it. Like it's kind of got some sense of how far it's moved, because it maybe can track how many times the wheels have rotated and stuff like that. And so there may be some kind of like side information about 3D position that you can use to help you in your estimation problem, right? So even if the robot's wheels are not like super accurate, you still may be able to get a nice initial position for the robot that you wouldn't have if you were doing like the camera tracking problem. What else? Also, the robot may have some additional sensors, like it may have some range sensors, like either it may have ultrasound or it may have actually like a little laser rangefinder where it can actually probe the world in 3D directly, which is something that the camera can't do, right? So you may have additional side information about the 3D world that's coming from, like, the robot has maybe some ultrasound sensors that are pointing at the walls, and it can tell it roughly how far away the walls are, in addition to what the camera is doing, right? One thing that's really important for SLAM, if I play this again, is that, here, one thing that's really important is as the robot kind of sees the same 3D points again as it moves around the world, it's very important to, I guess what they would say is close the loop, right? So you don't want to have the robot kind of estimating, let's see if I can draw this, it's probably easier. Right, so you don't have a situation where the robot kind of is pointing this way, and it estimates this as a 3D wall. Then it moves around here, and it comes back and estimates another 3D wall that looks like this, right? You want to make sure that all the stuff that the robot saw lines up. And so there's this kind of critical idea of recognizing when you've been in the same place, right? So there's kind of like this notion of, loop closure, or another way to think about this problem is drift, right? So, I mean, if you see the world, you come back and you've drifted, instead of going 360 degrees, you've only gone 359 degrees in the world of the estimation problem, then that's a problem, right? And especially for robot navigation, where you kind of want to say, okay, maybe I explore the world a little bit, and then I come back and I want to guide a user through the space, for example. You can't have this kind of weird doubling up of walls and stuff. So there's this kind of notion of, recognizing previous locations. And I don't want to, I don't really know enough to generalize about visual effects, but I don't think it's very common for you to have a visual effects shot where you're trying to match move and you're actually coming back to the same location. I mean, the only way that would work is if you were like twirling around or something like that, right? Usually a match move for a camera thing is going to be like a pan or a zoom or something like that, right? Okay, so I think that's about all I want to say on the subject. Any comments or questions? So certainly you will learn a lot about match moving yourself by trying to do it. I think that will make the concept a lot more tangible.